Hi everyone, this is Valli Rani, Department of Physics in Ramchandra College of Engineering. In this video, we are going to discuss about Newton's rings. Before going to discuss about Newton's rings, let me discuss the outcomes of this topic. At the end of watching this video, the student should be able to discuss or define the interference pattern formed in Newton's rings experiment. And also, the student should be able to describe how does the diameters of Newton's rings changes when air medium replaced by liquid film. These are the outcomes of this topic. Now we are going to discuss about Newton's rings. The Newton's rings is the best application for interference in thin films. The Newton's rings are circular form of interference pattern which was first observed by Newton, hence these are also called Newton's rings. Here the Newton's rings are formed because of interference by the division of amplitude between the waves reflected from top and bottom surfaces of the circular air film formed between the plano-convex lens and plane glass plate. The light rays reflected at the top and bottom surfaces of the air film or interfere and produce a series of concentric alternating bright and dark rings. This is about Newton's rings. Now coming to the experimental arrangement. The experimental arrangement of Newton's rings consisting of a plano-convex lens and plane glass plates, a monochromatic light source and telescope. In this, a plano-convex lens is placed on optically plane glass plate. This lens touches the glass plate at this point. An air film is formed between the lower surface of the lens and upper surface of the glass plate. Here, the thickness of the air film is gradually increases towards the edges of the lens and the glass plate. And at the point of contact, the thickness of the air film is 0. Here, S is a monochromatic light source. S is a monochromatic source of light falls on a glass plate G held at 45 degrees inclination. It makes the 45 degrees angle with vertical. The light ray reflected by this glass plate and allowed to fall normally on the circular air film. The instant light is reflected from upper and lower surfaces of the air film. These reflected light rays or interfere and produce interference pattern in the form of bright and dark circular rings. These rings can be viewed in microscope focused in thin films. This is the experimental arrangement of Newton's rings experiment. Now we will find out the path difference between these reflected light rays. Now, calculation of the path difference. To find the path difference between these two reflected light rays, here a monochromatic light beam is incident on the lower surface of the glass plate. This light ray incident at a point B on the lower surface of the glass plate. At this point, the reflected light is divided into two parts. A part of light is reflected back into the same medium and traveling along the path BE. And another part of light refracted into the air film incident at a point C on the upper surface of the glass plate. It will get divided into two parts at this point. A part of light reflected back into the same medium and traveling along the path CDF, and another part of light transmitted through this arrangement. Here, these two reflected light rays acts as a coherent light waves, and these waves superimposing and produce interference pattern with alternate bright and dark rings. Here we will find out the path difference between these two reflected light rays. Already we found the path difference between the light rays in reflected system is delta is equal to 2 mu t cos r plus lambda by 2. Here, for normal instance, r is equal to 0. Then cos r is equal to 1. Here the light rays are superimposed in air film. For air film, angle of refraction mu is equal to 1 and cos r is equal to 1. Hence, the resultant path difference delta is equal to 2t plus lambda by 2. So, this is the path difference between the light rays reflected at upper and lower surfaces of the films. Next, now we will find out the conditions for bright and dark rings. First we will find out the condition for constructive interference or for bright fringe. We know the condition for constructive interference delta is equal to n lambda. Here the path difference is integer multiple of wavelength, then we will get constructive interference. That means as a result we get the maximum intensity. Here is the path difference. 2t plus lambda by 2 is equal to n lambda. To simplify this expression, we get 2t is equal to 2n minus 1 into lambda by 2. This is the expression for bright ring, where n is the order of the rings. In the range, n is equal to 1, 2, 3. Here n is equal to 1, first bright ring. N is equal to 2 represents second bright ring. N is equal to 3 represents third bright ring, and so on. This is the expression for bright ring. Next, now we find out the condition for dark ring. Here the path difference is odd multiples of half wavelength, then we get destructive interference. As a result, minimum intensity will appear on the screen. Here the path difference 2t plus lambda by 2 is equal to odd multiples of half wavelength. To simplify this equation, we get 2t is equal to n lambda, where n is equal to order of the rings. N represents order of the ring. Here n is equal to 1, first dark ring. N is equal to 2 represents second dark ring. N is equal to 3 represents third dark ring. This is the condition for dark ring. Now we will discuss about properties of Newton's rings. In case of reflected view, the center of the Newton's rings is always dark, because in Newton's rings experiment, at the point of contact, thickness of the air film is T is equal to 0, and hence the resulting path difference is delta by 2, which is the condition for destructive interference. Hence the central spot will appear in dark color. But in the case of transmitted view, the central spot will appear in a dark bright color. While the order of Newton's rings increases, their radius increases and spacing between them decreases. If a monochromatic light is incident on the film, Newton's rings appear as series of concentric alternating bright and dark rings. Whereas in the incident light is polychromatic, those will appear with different colors as smaller wavelengths have smaller radius, vice versa. So these are the properties of Newton's rings. Now we will find out the diameter of bright and dark rings. Next, to find the diameters of Newton's rings. For this, let us assume a plano-convex lens is a part of the sphere. Here, r is the radius of curvature of lens. Let us choose a point P at a distance r from B. At this point, the thickness of the film is T. Now, to find the thickness of this air film at this point P, we can apply Pythagoras theory at this particular triangle OPQ. So OP, from the triangle OPQ, OP square is equal to PQ square plus OQ square. This is the expression. Here OQ is equal to OB minus QB. Here OB is equal to R and QB is equal to T. So OB is equal to R and QB is equal to T. Now substitute this value in above expression. We get OP square. OP square is equal to R square. OB square is equal to R square into OQ square is equal to R minus T whole square. Here R square is equal to Rn square plus here A minus B whole square. Expand this, R square plus T square minus 2RT. Here the thickness of the film is very small comparatively radius of curvature of the given lens. Hence T square can be neglected. Hence the resulting expression Rn square is equal to 2RT. From this expression, we get the thickness of the film T is equal to R square by 2R. Here we get the thickness of the air film. Now we will find out the diameters of bright and dark rings. To find the diameters of dark ring, for this already we found the condition for dark ring is 2T is equal to n lambda. Here we substitute thickness of the film T is equal to R square by 2R. We can simplify this. We get dn is equal to square root of 4n lambda r. Here dn represents diameter of nth dark ring. Here n represents order of the ring. This expression represents diameter of the nth dark ring is always directly proportional to square root of the natural numbers. This is the expression for diameter of the nth dark ring. Now we will find out the diameter of a nth bright ring. Already we found the condition for bright ring is 2T is equal to 2n minus 1 into lambda by 2. Here T is replaced by R square by 2R. Then we will get a final expression D is equal to square root of 2R lambda into 2n minus 1. Here dn represents diameter of the nth dark ring and n represents order of the bright ring. So diameter of the nth bright ring and n represents order of the bright ring. Here the diameter of the nth bright ring is always directly proportional to square root of odd natural numbers. This is the expression for diameter of the nth bright ring. Next. In examination point of view, these questions are covered as: explain the theory of Newton's rings. What are the Newton's rings? Why are they circular? Account for the circular shape of Newton's rings in interference pattern. Explain why the central fringe in Newton's rings in dark ring in case of reflected system. And explain the formation of Newton's rings and obtain an expression for the diameter of the dark rings in reflected system. And also this can be asked as show that the radii of Newton's rings are in the ratio of square root of the natural numbers, or show that the spacing of Newton's rings decreases with increasing the order of the rings. So these are the important questions asked in exam. By using this Newton's rings experiment, we can easily find out the wavelength of monochromatic light, a radius of curvature of the given plano-convex lens, and refractive index of the given liquid. These are the applications of the Newton's rings. This is about Newton's rings. Thank you.